Right, so very quickly, well, no, not very quickly. This is going to take a little bit. We're going to look at drift velocity, which is basically how fast the charge carriers are travelling when they move around the circuit. So charge carriers that we have in this circuit here are the electrons. My bulb, unfortunately, the filament has broken, but I'm going to give you some data about this filament in a moment so that you can do another calculation. But what we're going to try and work out is, as part of this circuit, when I switch it on, see we have current flowing here. Instead of the filament bulb, I've put myself the variable resistor to offer some resistance in the circuit, and here I have a thick copper bar. So what I'm going to do is I'm going to work out how fast the electrons are travelling when they move through my nice thick piece of metal bar. Now, what do I know so far? Well, one of the equations that I know, if I just move this out of the way ever so slightly, and we can still see everything. One of the equations that I know is that current in this metal bar is charge passing a point per unit of time. Okay, now there's going to be a certain number of electrons in the copper bar. Now, copper metal is quite handy because it's fairly easy to work out how many free electrons are in the copper, because when the copper atoms bond together, for every atom in the copper bar, a single electron is freed up. Okay, this is something to do with chemistry and valency and some guy Avogadro's number, none of which do we need to know. What we need to know is how many free charge carriers there are per unit volume. So we're going to call that n. Little n is the number of free charge carriers per unit volume. Okay, now if we're talking about a number of something per unit of volume, we could call that charge carrier density. Okay, so the free charge carrier density for copper is 8.5 times 10 to the power of 28 per meter cubed. Now, that is a pretty big number. Okay, but of course there are an enormous number of atoms in this metal bar and an enormous number of free charge carriers. Now, if I take a reading for current here I've got 0.77 amps. 0.77 amps. Okay, so now I'm just going to take a few pieces of this circuit out of the way so that we've got a bit more space to work. Let's take this out of the way. Now, what I've got is these charge carriers are going to be in a piece of wire like this. This has cross-sectional surface area there and a certain length of wire. It's going to have a certain number of free charge carriers. Now, how do we work out how many free charge carriers? Well, area times length is going to give us a volume. Okay, and we've got how many free charge carriers there are per unit of volume. So A times L times the number of free charge carriers per unit volume is going to tell us how many charge carriers we have in this piece of wire. And then the amount of charge current is the amount of charge passing a point per unit of time. So that amount of charge in this bit of wire is going to be the number of free charge carriers times by the charge on each individual charge carrier. So big Q there, I've used little q here. Now these charge carriers are electrons, so therefore area times length times the number of the charge carrier density times the charge on each charge carrier is the charge on an electron, or E. Okay, this is going to be the total amount of charge in this volume of wire, and if this amount of charge is moving through the wire, it's going to move with a certain velocity. So let's remind ourselves, the equation for velocity is going to be displacement divided by time, or in this case it's going to be the length of the wire that the charge carriers have travelled down divided by time. So length divided by time. So let's start putting these equations together a little bit. For example, current is I, and that's charge divided by time. The total amount of charge in this length of wire I've got here, so that capital Q is going to be equal to A times L times N times E. And time, well, here I can rearrange the velocity equation to have time is equal to length divided by velocity. So instead of having time on the bottom part of the equation, I can have length divided by velocity. That's L, not E. Okay. Now, what happens when we divide by a fraction? The bottom part of this fraction is going to jump up to the top. So we're going to get I is equal to A times L times N times E times V, all of which is divided by L. So length cancels out and I get current is equal to A times N times E times V, and this is the equation for drift velocity. I've already got value for current, it was 0.77. Cross-sectional area I can work out by measuring the diameter of my bar in a number of different places. So the diameter is you see this? I've got 1, 2, 3, 3.17. Let's try somewhere else. Different place, different orientation. And I've got 3.17, 1, 2, 3.17 again. Third time lucky. .18, 3.17, 3.17, 3.18. Okay, so I'm going to use this data now. I've got current. I can work out cross-sectional area using my diameter measurements here. I know the number of free charge carriers because of using a bit of chemistry and some guy's number. I know the charge on a free charge carrier, so then I can work out how fast these electrons are travelling on paper. Okay, and then I'm going to give you some data about the tungsten filament in this light bulb. So for the same current, you can work out how fast the charge carriers are travelling in that tungsten filament. Okay, so this video is going to go with a Google Doc. Enjoy.